Today, we are doing rectangular approximation method. You will see the phrase Riemann sums thrown in here as well. Those mean the same thing. Okay, when I say Riemann sum or rectangular approximation, it's the same thing. It's just one was discovered by the guy, and instead of using RAM, they use Riemann. Okay? So, for the first problem here, it says readings from a car speedometer at 10-minute intervals during a 1-hour period are given in the table. Use LRAM with 3 subintervals, approximate the distance traveled. Okay, so imagine what's going on here. Somebody's driving their car. At time equals 0, they look at their speedometer and it tells them 26 miles per hour. Then they're driving for at 10 miles, or at 10 minutes, they look down, they're going 40 miles per hour, and so on. They're just writing them down. Okay? They normally would not, they normally just give you this table right here, but I was nice to you, and I graphed it out for you. Okay, here's a graph of it. Let's just connect the dots. Even though I have no idea what's happening in between. Maybe they drove real fast and then slowed down to get to that point. I'm just going to assume straight lines here. Okay, so this is kind of what this person did. It looks like they slowed down for a while, then sped up, then slowed down, and then sped up. They were all over the place. Must have been heavy traffic. See what's going on there. Our job is to use a left Riemann sum, a left RAM, left rectangular approximation, and make 3 subintervals. How far am I spanning total? 60 minutes. I'm going from 0 to 60. So if I want to split 60 minutes up into 3 subintervals, what am I going to do? 20. So on my graph down here, I'm going to draw a line every 20. That means I'm drawing one on the outsides, so at 0 and 60, and then every 20 in between. So 0, and then at 20, and then at 40. Now we've split this thing up into 3 subintervals. One between 0 and 20, one between 20 and 40, one between 40 and 60. It's the between that we care about. Okay, that's what we're thinking about here. So looking at this first subinterval, we're going from 0 to 20. We're doing a left RAM, okay, left Riemann sum. So which one of these dots are we going to use? Are we going to use the red one, this red one right here? Are we going to use the blue one? Or are we going to use the green one? The red one, because the red one's on the left. So that's the dot we're using. We're going from the left side across, and it's going to make us a rectangle. So this right here is the first rectangle that I have. My next subinterval goes between 20 and 40. Okay, if I'm going in between 20 and 40, which one of these 3 dots am I going to use? Am I going to use green? Am I going to use the black one? Or am I going to use the blue one? Oh, just kidding. The blue one. The green one. The one on the left. Yeah, that guy. Okay, we're going from that side over. So it's giving me this right here. And we got one more dot to go. We've got blue, we've got orange, and we've got pink. In that last subinterval between 40 and 60, which dot are we going to use if we're doing a left Riemann sum? The blue, the one on the left side. If we're doing Riemann sum approximations, that means we are finding the area of all 3 of those rectangles and we're adding them up. That's it. Okay? Visually, that's what we're doing. But we're not often going to get a graph. In fact, you're very rarely ever going to get a direct graph on these problems. Okay? So let's show you how to do them on a table. This is what we're trying to do, but we're going to do it from the table only. Okay? This first part might seem silly. Make eye contact with me. This first part might seem silly, but this is how you're going to get it correct. Okay? I need you to do this on your paper because otherwise you're going to screw it up. Okay? We're going from 0 to 60. The first subinterval goes between which 2 numbers? So what I want you to do is on your chart right here is to draw a line that connects 0 to 20. Not from the lines, but from the number 0 to the number 20. Okay? We just made the base of a rectangle, just like we did here. We went from 0 to 20. We drew a line across. Same thing going on there. Okay? Our next one is going to go in between which 2 numbers? So I'm going to draw a rectangular top here in between 20 and 40. These might seem silly, but it is going to allow you to get the right answer, 20 to 40. And then our last one goes from 40 to 60. Makes sense how we split this into 3 subintervals. Now let's do it. Okay, we're doing this whole thing to help us approximate the total distance traveled. This is the trickiest Riemann sum problem I've ever seen, and it's not tricky. Okay, notice what we've got here, though. Look at our units. Time is in minutes, and our rate is in miles per hour. Are they the same? No. We have to do a little bit of conversion. Okay, this is as tricky as I've seen, and it's not hard. Let's just convert minutes to hours. If I'm going from 0 to 20, how wide is my interval going to be in hours? It is 1/3, because it is 1/3 of an hour if you go 20 minutes. So that is my width, 1/3. And then I'm going to work on the height. Okay, I'm doing the height. So understand what we're looking at. We're looking at these 3 numbers. Okay, the ones that go between 0 and 20. Which one of those numbers am I using if I'm doing a left Riemann sum? Which number is on the left? 26. That's my height. Okay, that's the height of this rectangle we drew down below. It was 26. So 1/3 times 26, that's my first one. Okay, then we're doing my next subinterval. What's the width of the second one in hours? 1/3 again, because I'm going from 20 to 40. That's 20 minutes, so it's 1/3. Here are the 3 numbers, 55. Let's do the same color code so we can see what's going on. 55, 10, and 60. Okay, 55, 10, and 60. Which one of those numbers is on the left? So 55 is going to be the height. That's, again, down below. When we drew this, that was the one we used, the 55 height. And then our last one, the one that goes from 40 to 60. We're using these 3 numbers right there. The width is 1/3 still. Which number are we using, 60, 32, or 45? The one on the left, 60. If this was a free response question, you then stop and you celebrate that you have got it correct. Okay? You don't need to do anything else. Okay? I hate grading these tests when kids just leave them. I would much rather you get the right answer and I can just see the number and know that you did it all right. But I'll survive. Okay? I would rather actually have to look at them all, and I'm okay with that. Can we do anything to factor out? Is there anything that all 3 of them have in common? So if you took a 1/3 out, you could rewrite this as 26 plus 55 plus 60. And so if you did have to do it, that would make it maybe a little bit easier. Anybody actually type that into your calculator? 47. Okay, so know what that 47 means. We started with miles per hour. That was what this black graph was down below. And we found the area under the curve. It's not right. You can see that there's a whole lot of error there. Okay, but it's approximately telling me what? We started with miles per hour, and then we found the area under the curve. That is telling me miles. That is the amount of miles that we traveled in that 1 hour period. When you find area under the curve, it'll tell you in an amount. Make sense so far? That one's the worst one of the day. Everything else is way easier than that, and that's not bad. All right, let's do the next one. Kathleen, so all these questions today are from an AP exam. This one's from 2016, I think. Kathleen skates on a straight track. She starts from rest at the starting line at time t equals 0. From 0 to 12 seconds, her velocity is measured in feet per second. It's differentiable and it's increasing. The table tells you what's happening. Use a right Riemann sum with 4 subintervals indicated with the data to approximate that thing. And then we're going to do units of measure and talk about over-under approximation. So, we've got Kathleen. She's going skating. This tells you her rate. And this tells you her rate at different times. That's the setup that we've got right here. So our job is to approximate the integral of 0 to 12 k of t dt. Or in other words, we're finding the area under the curve from 0 to 12. The way we're doing it right now is an approximation, so it's not perfect. So we're just approximating here. Right Riemann sum and 4 subintervals. So looking at that chart right there, I'm supposed to break it up into 4 parts. How many numbers did they give me? Oh no, they gave me 5 numbers, but I'm trying to split into 4 parts. That doesn't work. Yeah, it does. Don't let that bother you. Where's my first interval going to go from? 0 to 3. And then my next one is going to go from where? 3 to 5. And then the next one is from 5 to 8. And the last one is from 8 until 12. Oh, you need 5 numbers to make 4 intervals. Okay, that's a thing. Did you just draw the tops on your graph? Because if not, I don't like you anymore. Draw the tops on your graph. It helps you understand it. Okay, are these all the same interval? Are they all the same width? No. 0 to 3, 3 to 5, not the same width. That's okay. That's the data they gave me. I'm going to live with it. Okay, let's look at that first one. Okay, so we're thinking about these two numbers right here, this 0 to 3. We're doing width and we're doing height. So if I'm talking width right there, Andrew, how wide is that first interval going to be? 3, because to go from 0 to 3, his width is 3, and then he's going to multiply that by the height. So he is looking at these two numbers. Okay, it's either 0 or 5. Which number is he going to pick if he's doing a right Riemann sum? The one on the right. He is picking the 5 that goes with that. So it's 3 times 5 down below. Then we're doing the next subinterval. So from the next subinterval, from 3 to 5. Kirsten, how far am I going? What's the distance between 3 and 5? 2. So she's adding to that 2 times. And then you've got these two numbers, 5 and 10. Which one do you want to pick if you're picking the one on the right? 10. 2 times 10. Sarah, what's the width of my next one going to be? 3, because she's going from 5 to 8. What's your height going to be? 20. She's picking the number on the right on that interval, so it's 20. And then our last one here, Martha, what's the width of my last interval going to be? 4, because she's going from 8 to 12. Which number are you picking? The one on the right. It's 24. Done. That is my answer to this question. Okay? I don't have to do the actual math. I just approximated the interval by doing a right Riemann sum. Can I factor a number out of everything? No, because unlike all the other ones we've done so far, they're not equal subintervals. 3, 2, 3, 4. Cool, so that's really the simplest I could make it. Okay? If you had to, you could calculate it. Anybody get a calculation here? I think it's 191. It's 191. They did ask us for units. 191. The rate was in feet per second. So that 191, what would my units be on that? It would be feet. It's 191 feet. Because when we integrate, it tells you the amount of whatever that rate was looking at. Okay? It's 191 feet. Or in other words, she started at 0 feet. 12 seconds later, she's traveled 191 feet. That's what we just found out. Make sense? The third part of this question is it an over or an under approximation? Talk with your neighbor for a second. See if you can understand what you think it's going to be. Let me see. Thumbs up if you think it is an over approximation. Thumbs down if you think it's under. I will say that as a calculus teacher, I have taught this a long time, okay? I still struggle with this, at least in my brain, okay? I can't just look at this problem and tell you immediately, oh, that's over or under, okay? I'm going to draw it just like you should, okay? This is an over approximation. So I would want to draw these things out. What do you think? A lot of us said it was an over approximation. Why did you think it was an over approximation? Cole? That's the perfect combination. He said both things. There are two things that are going to tell you if it's over and under. Okay? The one thing you got to look at is whether or not it's increasing or decreasing. Okay? If you don't know if it's increasing or decreasing, you can't help it. So you've got this on your paper where it's increasing and decreasing. Draw a picture in the increasing category. Draw a picture of an increasing graph. Draw one for each one. Okay? It can be whatever you want. As long as it's continually increasing, you're good. So I'm going to draw this cool little concave down and concave up. Fancy. And there's that one. Doesn't matter what you draw. Okay? We're going to draw two different versions. We're going to draw right ram and we're going to draw left ram. Understand what that means. If it's right ram, that means the right corner of your rectangle is going to touch the graph. Okay? So it doesn't matter where you're on your graph, but I'm going to touch the graph somewhere on the right side, and I'm going that way and making my rectangle. Okay? So it's got to be anchored on the right. So then I'm going to go up a little bit and then go over until I touch the graph again. I'm going to go up a little bit and then go over to the right until I touch the graph again. That is a right ram problem. Is that over or under? That is over. That is what we just described. How did you know that my graph was increasing? Because it tells you. Okay, right here it says it's increasing. Don't overthink it. What if it was LRAM? So if it's LRAM, that means you're going to start on your graph and then go to the right a little bit and then you go down. Oh, that's weird. Don't do that. Oh, that's fine. There's that. Go up to my graph and then go over to the right and go down. Go up to my graph and then go over to the right and go down. If it is LRAM and increasing, is it an over under approximation? Under. You're underneath it. Draw two decreasing graphs. I would do the same thing. I would just graph it out because it's hard for me to see it. And I'm just going to draw the most basic ones. Again, if it's RRAM, I'm going from the right side. So if I go to the right side and down, right side and down, right side and down, it's an under approximation. If it's LRAM, I'm going from the left side over, the left side over, the left side over. It's over. I do not have that memorized. I would look at my graph and see, is it increasing or decreasing, and then go from there. That's the key to your success. Question so far? Flip it over. Reading on the back side, again, this is from an AP question. Hot water. Hot water is dripping through a coffee maker. Fill in a large pot of coffee. The rate of coffee in ounces per minute at time t is given by that differentiable function. So it's telling you the rate of coffee, where c is measured in minutes. Use a midpoint sum with 3 subintervals of equal length in order to approximate. So our job is to approximate from 0 to 6 the coffee. Okay? We've got that interval. It goes from 0 to 6. We are splitting it up into 3 equal subintervals. So if we're doing 3 equal subintervals, 3 subintervals equal length, how far is each one going to be? 2. So draw your hats on your graph. Okay, draw your connectors. Draw your connectors on your table. So my first one is going from 0 to when? 0 to 2. And then from 2 to 4. And my last one from 4 to 6. So my first subinterval, we're approximating here. Our first subinterval. Lydia, how wide is that first subinterval going to be here? It's 2, because she's going from 0 to 2. So she's starting off with 2, and then she is multiplying by her height. So as she looks at this, there are 3 numbers to pick from. 0, 5.3, or 8.8. Which one are we going to pick if we're doing a midpoint sum? The one in the middle. Do the rest of it. So not a very hard question. The widths of all of them are 2. You could find the middle number between, so 11.2 and 13.8. Boom. We could factor out a 2 if you really wanted to, but that is my answer. Again, if this were free response, I'd leave it right there. Okay? Anybody have a calculator out and actually do it? 60.6. What would the units be on that 60.6? Ounces. They started with a rate. We integrated it. We found the area under the curve. It tells us an amount. Ounces. Okay? So if there is one thing you want to get from today, it's this. When you find the area under the curve of a rate, it tells you what? An amount. It is an integral. It tells you an amount, just like that last one. We took the rate of coffee when we integrated it. When we found the area under the curve, those mean the same thing. We found an amount. That is the amount of coffee in the pot. Okay, last ones of the day, and these are easy. These will take us 2 minutes apiece, if that. In a marathon, when the winner crosses the finish line, many runners are still on the course. So imagine us running a marathon. Obviously, I'm going to win. I won the marathon. All of you are behind me. Okay? The density of the runners, X miles from the finish line, is given by that equation. So you guys are all spread out. That equation will tell you the density, or in other words, how many people per mile. Okay? So this right here, R of X, is a runners per mile. It is a rate. How many runners are within 8 miles of the finish line? They gave you a rate, runners per mile, and they are asking you for runners. What are you going to do with that rate? Augie? You're going to find the area under the curve. And right now, We can do that with our calculator. We can integrate that thing. From when to when do you think you want to integrate it? 0 to 8, because from the finish line to 8 miles back. We are going to integrate what? R of x, that rate. And we do have a dx in there. I know you're not super familiar with that, but it's always the rate with a dx or a dt on it. That's what you're doing. You're just typing that into your calculator. Okay, do that real fast. Which button are we using to find that thing? Math 9. You get this cool little integral symbol. You go from 0 to 8. Inside the parentheses, we're going to type that equation. This one's kind of ugly. All right, I might suggest typing this in as y1. That way you don't have so many parentheses. But let's act like you can type stuff in. 20. And then parentheses, 1 minus cosine. And then it's parentheses. Oh, there are parentheses already there. 1 plus 0.03 x squared. Close my parentheses. dx. Hit enter. Boom. There's my answer. 166.396. What is the units there? That is runners. Okay? And I know the exact question Spencer's about to ask. Spencer's going to ask, should I round to the nearest runner because there aren't half people? No, don't do it. Okay? We don't round unless they tell you to round. Because maybe on this one person is like 8 miles, and so they're close to getting past the 8 mile, but the line kind of cuts them off. It's only 0.396 of them cross it. We don't care. It is not our job to interpret the question. It's our job to do the calculus. On a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by that equation, where T is measured in hours, and 0 is less than or equal to T is less than or equal to 24, where 0 corresponds to midnight. Find the total amount of unprocessed gravel that arrives at the plant from 3 to 1 during that workday. Go, do it with your neighbor. On a certain workday, the rate, they are giving you the rate in tons per hour of gravel. We are trying to find the amount of gravel. The rate is given by this G of T equation. What are we going to do with G of T to find the amount? We are integrating that guy. We integrate a rate. So we're going to integrate G of T here, dt, and that's going to tell me an amount. From what numbers am I going to integrate this thing from? It is from 3, because 3 a.m., to 1 p.m., which is 13, because 0 is midnight, so 1 a.m. is 13 hours after midnight. Then all you got to do is type that into your calculator. Boom, 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 boom. A lot of button pushing. Somebody get us an answer here? 890.683, because we always go to 3 decimals. That would be bad if we didn't. What is that? What is the units here? This is tons, because it was in tons per hour. When we integrate it, it takes us down to just an amount.